thank you very much to IPET and our host for inviting me for this lecture. And I wanted to mention that I have a long history in Korea, and I've been welcomed back by some very close friends for this visit. And some of them are in the audience. So Professor Chae Hong Lim recently retired from Seoul National University, but invited me here in 1995, I believe it was. And I came back and visited many times. And Professor An Hee-Kwan, who's now a professor at Cheongnam National University, is here, and he welcomed me back and is here in the city. And Director Park Chi-ho, who's with a National Livestock Environment Program very close by as well. So it's been a really great opportunity for me to be back and to see them and the people they work with and to visit. I'm going to talk about renewable energy, but also about carbon negative energy, which is something that agriculture and forestry can provide that really no other sector can provide. And I think that's going to be increasingly important in the next few decades. So I wanted to give you a bit of a preview of that. I'm going to provide that from a U.S. perspective. And let's see, oh, sorry. All right. But I want to start by a set of slides that I was first exposed to when I was in college in the 1970s. So that would be about here. And this is some data on CO2 in the atmosphere taken at an observatory on the island of Hawaii that has had continuous recording since about the time I was born. And obviously the carbon dioxide levels in the atmosphere have been increasing, but what I want to draw your attention to is, sorry, get this figured out, to the fact that there are these cycles each year where the emissions increase due to fossil fuel emissions, but then every summer the northern hemisphere has so many plants growing that they take a lot of that atmospheric CO2 back out and put it into biomass. And that's happened every year for millennia. And that downward arrow, the power of photosynthesis to take CO2 out of the atmosphere, is almost as big, not as big, but almost as big as our ability to put fossil emissions into the atmosphere. So that's a fairly extraordinary fact. And I think it gives us a lot of hope in agriculture and forestry that we are a part of the solution to the climate challenges. This is just to illustrate that the fossil fuel emissions are relatively steady, but atmospheric CO2 increases each year, whether that's 1 part per million or 2 parts per million. Those are occurring at a much more variable rate, and that's because of the variation in photosynthesis. So this is a very powerful force, but it doesn't always happen. And both natural cycles, but also human management can do a lot to make sure that that's beneficial for us. This slide just illustrates the scale of the challenges. Humans have emitted about 2,800 gigatons of CO2 equivalents since the beginning of the industrial age. Now, if we want a really hot climate, 8.5 degrees hotter than it is now, then we might emit another 11,000. But the goals now are to keep it lower, and we think that that's going to be with a total cumulative emission of something like 4,660 gigatons of CO2. And if we do the subtraction, that means that we've only got something less than 2,000 gigatons left, and we're putting out 50 a year. So this is happening very quickly. We need to move forward quickly to change this. And the estimates by the IPCC and others have been that we have to start first reducing our emissions, and the upper part of this pink curve are the fossil emissions that are projected at a very aggressive substitution of renewable energy and energy efficiency for fossil emissions. But also, to get to this black line, which is the projection that we need to get to limit atmospheric CO2 and climate warming, we have to start to produce what are called negative emissions. And negative emissions are something that solar and wind cannot accomplish on their own. These are CO2 molecules in the atmosphere today that have to be taken out of the atmosphere permanently and put someplace else. And there are a number of different mechanisms by which that is possible, and I don't think they've gotten nearly the attention they can, but in this IPET and this group here, I think you'll have an appreciation for them. So just a quick summary. U.S. has been driven by fossil energy for the last half century and more, coal, natural gas, and oil. There are changes that have occurred. Both oil and natural gas have been increasing rapidly because of hydraulic fracturing. So the U.S. is no longer an energy importer, but we're now an energy exporter. A lot of that has been substituting for coal domestically, although we do still use quite a bit of coal. And our nuclear energy has been very flat. We've tried to ease the permitting process, but that has not been successful. Nuclear energy is very expensive, large capital costs, and so it doesn't seem to be growing very, very quickly. But renewable energy is growing, and it's growing quicker than this chart would illustrate because it started at a very small base. Most of the renewable energy until the last few years has been hydroelectric energy. So those were big dam projects that were built over time, and the solar and wind that we think about as the new renewable energy are very recent. So this is our current portfolio of all energy sources. You see we have some biofuels, corn ethanol, hydroelectric still an important part. Solar and wind still relatively small, but growing rapidly, as you'll see, as is bioelectricity. And I did want to note that when we look at our U.S. energy portfolio, this is the energy efficiency component that has been established since the 1970s. And you'll notice the biggest part of our energy supply. We don't ever talk about it because it's negative watts, but it's a very important part of the picture. This is a busy figure. These are, by the way, in your booklet, so I won't spend a lot of time on it, but this is just to illustrate the total portfolio of energy in the United States from the renewables and the expected changes. And I think the important thing to note here is that wind and solar are increasing, and the solar is increasing faster than the wind. So the expectations are that that's going to continue to be the case, and in the next few years, we'll be adding more solar than we are wind each year. Solar is becoming very cost competitive, as is wind already with our traditional fossil energy resources. We are still doing things with hydropower. So this is a flood control dam that existed and was built for flood management and now has been retrofitted with energy production so that energy storage that's represented by the water behind the dam is now able to provide us with electric power. This is a map of the U.S. wind resource. As you'll see in the next slide, a lot of the wind is in the center part of the United States. This is rural America. This is the heartland. When people talk about farm country, it's also wind country. And so that's been a tremendous opportunity and is part of why wind energy has gotten a lot of political support in the United States. I did want to note that there's also very high wind offshore on both of the coasts and also the Great Lakes of the United States. And Korea, as a nation with a lot of ocean, probably also has a lot of offshore wind opportunity. These are the wind farms in the United States. Again, you'll see from West Texas through the Corn Belt, all the way across to the rural east and also the rural west. Lots of wind farms that have been built, and they're still going up rapidly. And we call them wind farms because they're often on farms. There are also a lot of wind towers that look like rows of corn in some cases. Oh. Sorry. All right, so solar has also been increasing rapidly. And solar has been increasing so rapidly that the people that predict solar growth have been missing the growth every year for more than a decade. So this is just a list of the World Energy Outlook that is put together by the International Energy Agency. And these are their projections starting in 2006. And every time they take a point and they project what's going to happen to solar, it's flat or it grows slowly. And actually, for the last 5 years, they expect the growth to decrease every year. And instead of being flat or decreasing, it goes up, and it goes up, and it goes up, and it goes up. you would think that after 10 years of this, they would notice that their projections are always wrong by a massive amount. So this is not purely because of policy. This is because of economics. The drop in the cost of solar energy over the last decade has been phenomenal, and it has not stopped. And that will continue, and it's rapidly becoming cost competitive with solar, with fossil fuels, even in areas that are not that sunny. Now, with solar, we do tend to put them in sunny locations, and in the U.S., they're often dry locations. Here's that U.S. growth in photovoltaics. You see that between 2015 and 2016, the capacity of solar in the U.S. doubled in a single year, the new capacity. So our growth rate doubled. We did have an election you probably heard about in 2016, so there's less policy support, so things slowed down a little bit. But 2018 is projected to be up in this range here. So it's rebounding. Here's an illustration of a typical solar farm in the U.S. We call them farms also because they're in rural areas. They're not often on agricultural land, and that's because they have to intercept the sunlight, and so unless you've got excess sunlight, which is not very common, it doesn't really make sense to do them on the same land. But oftentimes, it's a very compatible use in rural areas, and that's happening a lot in the U.S. All right, so I've already showed you this slide, and I've come back to it because I want to spend a little bit more time on this negative emissions concept in the context of agriculture, forestry, and biomass energy systems. So first I want to talk about what are called natural climate solutions. So these are mechanisms to draw down atmospheric CO2 that don't necessarily have much to do with the energy systems at all. They're ways of doing climate-smart farming, of managing forests so that we can use the trees to capture some of that carbon. And estimates are that natural climate solution strategy might be 1/10 of what we need by 2050, but in the near term, it can be up to half of what our needs are in terms of getting the atmospheric CO2 reduction that is estimated to be needed. Many of these strategies are very cost effective right now. They also oftentimes have ancillary benefits to farming and forestry. And so these are important to look at. I also want to note, though, that our farming and forestry can have positive benefits, but they can also have negative costs around climate. And this is the global carbon or global warming budget. Many of you have seen these Sankey diagrams before, and up here is the energy supply, but roughly 1/3 of the global warming emissions, both CO2, methane, and nitrous oxide, are associated with land use change and agriculture. And I will note that the methane, which is largely associated with agriculture, coming from rice paddies and livestock systems, actually creates a big opportunity to reduce those existing emissions as we build better biomass energy systems and better farming practices. And similarly, nitrous oxide is largely associated with agriculture and agricultural fertilizer use, which again, we have opportunities in the agricultural sector to change our management strategies and make a big reduction in global warming emissions. Okay, so this slide here is meant to illustrate that within a natural ecosystem, there are very different amounts of carbon that are stored. So this is all on, it's megagrams of carbon per hectare. And you see that our wetlands and tropical forests, and actually forests in general, all hold a lot of carbon compared to our managed landscapes such as cropland and grasslands. And that a lot of this carbon is above ground in the forest ecosystems, so roughly half in temperate forests and more than half in tropical forests. So when we hear about rainforest destruction and land use change and deforestation, that's what we're talking about. All of that carbon that's stored in the above ground biomass. And it's a substantial amount of material. If we take a forest like here in Korea and we turn it into cropland, we're going to roughly reduce by half the amount of carbon that's stored. If we take cropland and turn it to forest, we can double the amount of carbon that's stored on the land. So we have to be very thoughtful about the way we manage landscapes, and they create really easy opportunities to deal with climate solutions. But we're humans, and we like to manage land, and so the question is, how can we be smart about what we do? Well, we're changing our forest practices in the United States, and this is the forest accumulation of carbon now. Most of these forests are still being managed as commercial forests. We didn't turn our whole country into a national park. But these commercial forests are being managed with longer rotations, and they're capturing more carbon, and they're capturing at the order of maybe 100 million megagrams, metric tons per year, in the forests that exist. And we're also seeing cropland and other land revert to forest, and that's another 30, 50, maybe 70 million tons a year. So these are big numbers that are happening with minimum intervention and minimum cost. This is an illustration of a whole list of natural climate solutions. I apologize for the small print, but this is in the handout. Here are all the ones in forest, and you can see reforestation is having a tremendous potential to reduce CO2, atmospheric CO2 overall. Lots of different management opportunities with plantations. But I also wanted to bring your attention to the different agricultural and grassland strategies in terms of improved rice production, conservation agriculture, better grazing, better nutrient management, agroforestry where we're incorporating trees and croplands, and biochar. All of these have great potential to use agricultural systems and agricultural management to reduce climate. We can also do that with our biomass energy systems. And this is a complicated slide. I'll take you through it slowly, but it shows the flexibility and the opportunity to, in biomass energy systems, to store organic matter both in the soil, but also underground in geologic formations. And that's called carbon capture and storage. And it's something which, a technology that was largely developed for the fossil fuel industry. So in the United States, all of the research on carbon capture and storage is coming out of the fossil energy budget of our Department of Energy. But it turns out the only commercial carbon capture and storage project in the United States today is a bioenergy carbon capture and storage. And ADM, Archer Daniels Midland, is now capturing 1 million tons a year of CO2 off of their fermentation of corn ethanol and putting it deep underground, about more than a kilometer underground, into a geologic formation. And they're making money doing that today. Oh, sorry. Okay, so let's start with the plants. Photosynthesis is a greatly underappreciated technology. It's a biotechnology. It's a little over 3 billion years old, so we can't take a lot of claim for it. But it takes solar energy, and it takes carbon dioxide at very low concentrations and turns it from a gas to a solid. So that's very powerful. So what do we do with that powerful technology? Well, typically we make food with it, either by directly eating the plant material, or most of the plant material in advanced countries like Korea and the United States goes into meat production, one way or another. And so most of that carbon then goes into our livestock systems, and then most of it goes into our manure systems. So that photosynthetic carbon is either going into food, to roots of crops, which can help encourage soil organic matter, or through our livestock and our manure, and then potentially into our soil organic matter as well. So these are all opportunities to capture the CO2 through natural systems and natural management. And as the previous slides illustrated, these are not small opportunities. They're very substantial, they can be cost effective, and I'll share with you some examples of that. We can also take a bioenergy facility, and this could be a combustion facility for bioelectricity, but I think it's more attractive right now to use biological processing because they provide a more concentrated carbon dioxide stream. So if you're running a corn ethanol facility, you will get 100% CO2 as a natural byproduct of that process. If you're running a biogas facility, 40% of the carbon, perhaps more, is going into CO2. And those concentrated streams provide a nice opportunity to do something creative with carbon. It could go into a geologic formation. That CO2 can also be used in manufacturing, and there are now a number of technologies to turn captured CO2 into plastics and biomaterials. So you take that plant and you capture either a combustion plant, the flue gas, or a biogas plant, the biogas, or a fermentation plant, the off gas of CO2, and that needs to be sometimes cleaned up a little bit, chemical separation processes, although those later examples, not very much. And then that can be compressed and put into a well and pumped into the ground into a geologic formation. And these formations are either saline aquifers, or there's a number of different types of geologies, sandstones, basalt formations that are very effective at CO2 sequestration. So here's an estimate that was done earlier this year by Dan Sanchez and collaborators at Stanford University. And they did an analysis in the United States of where the CO2 storage geology was best. So all of these light blue areas are areas where we have, we think we've got really good geology for CO2 storage. And then these red dots are all of our corn ethanol facilities. And this paper, and I'd be happy to share the reference with folks, considers that right now in 2018 and 2019, it's now cost effective with our current carbon policy in the United States, which does not have a strong incentive for carbon reduction, to take the CO2 out of these agricultural systems, these corn ethanol facilities in the Midwest, and put it into pipelines and put it into geologic storage. And that can take the offsets associated with these systems and dramatically improve them. The estimates are that that can be done for about $35 per ton of CO2. So those of you working in that area, that's a pretty reasonable cost. That was work at Stanford. I'm going to share some work that I've been doing with colleagues at Colorado State University and Dartmouth College. And we've been developing a systems framework to look at these different options. So one of the things that comes up in bioenergy systems is we want to make a comparison between what we might manage and what might happen naturally. So I've already shown you evidence that the forest can do a pretty good job on its own with no human intervention. So we modeled that for a number of different forest systems in the United States, and this is basically that analysis. We look at the forest as an ecosphere that has both above ground and below ground carbon. We know how much net primary production is pulling CO2 out of the atmosphere. We know how much of that is respiring back into the atmosphere through decomposition processes. And we also know how much emissions when we let the forest grow on its own or agricultural lands grow on their own, we also know how much fuel we're going to need. And this is the tailpipe emissions, and this is the gasoline supply chain emissions that are both going to go into the atmosphere if we don't make biofuel. We can reduce that by a biofuel system where we still have the ecosphere. We're still taking a different amount often of net primary production and a different amount of respiration, so that exchange is different but similar. And then we also have something we call a net ecosystem carbon balance. And in this case, we're going to harvest the above ground biomass to make some kind of biofuel, at which point we will have a biofuel, a biorefinery emission, and that may or may not be captured, and a tailpipe emission from the biomass, which is going to go back to the atmosphere, and then the potential for carbon and capture and storage to put some of that into the geosphere. okay? So that's a bunch of definitions for the analysis of the results I'm going to share here, which are for a set of different ecosystems in the United States that are currently in pasture, cropland, and secondary forest. That's not primary forest. It's been cut at least once, oftentimes several times. We looked at current cellulosic biofuel technology, future cellulosic biofuel technology, and this could be biogas, and future cellulosic technology with carbon capture and storage, as I illustrated a few slides ago. We also looked at the native systems, either allowing forests to regrow or in areas where there's not enough moisture in the United States and some of the plains states, allowing native grassland to regrow. And then we looked at all of the positive and negative emissions factors that include the avoided fossil fuel emissions, the biomass supply chain emissions, the captured ecosystem or ecosphere above ground and below ground carbon, and the potential for CCS in some examples. And we added those up, plus and minus, to calculate a net mitigation for each system, okay? And what you see is those natural systems do pretty well, but when you look at current cellulosic biofuel technologies, and that would be biogas or cellulosic ethanol today, they're more powerful as a climate mitigating factor on the sites we looked at in the US. If we look at the advanced biofuel systems, and these scenarios look at increasing crop production, so our bioenergy crops are growing faster, they've gotten breeding, we're looking 20 or 30 years out. Some changes in technology as well. We can get that up to being a bigger level. And then what's interesting is if we add CCS to that, we can almost double the net benefits of the whole system. And that's because 1/3 to 1/2 of our carbon in our current biofuel systems is lost to the atmosphere at the biorefinery or biogas location. This is some other work, actually by the same author as did the pipeline work, Dan Sanchez, but when he was a graduate student at UC Berkeley. So another carbon capture and storage strategy, and in this case, looking at electricity. And these are carbon negative scenarios where in the western United States, if we look at all the electricity and use the waste carbon from forest residues, from crop residues, from construction waste, and from food waste, and put that into electricity systems, we can get negative emissions, depending on the goals and the prices, that exceed the 86% limitation that is required by California law, and get down to 100, 120, 145% negative from what things are today. Now that's with, and this is interesting, 14% of the electricity portfolio from all those waste biomass with carbon capture and storage. And the other 74, 75% is largely solar and wind. So it's a complementary strategy for different types of renewables. I also wanted to quickly mention that in addition to the energy option, there's many great material strategies for using, for example, wood as a construction material, substituting for concrete and steel in different types of construction processes. And the net CO2 reduction per kilogram of wood fiber used is actually better for materials than it is for energy. So when we think about our forest and agricultural land, we need to remember that there's materials opportunities too, and those should be considered very carefully. Oh, sorry. This is an assessment of the biomass potential in the US. You can see lots of crop residues, manure, urban waste, forest residues, and perennial crops. And I wanted to add to that winter crops, which I think may have some potential here in Korea, and definitely has a lot of potential in the Midwestern United States, where our land is fallow for almost half of the year. I'm not going to spend a lot of time on this slide because I'm running out of time, but just to note, the International Energy Agency and others are projecting that by 2050 and 2075, biofuels need to be a large part of our transportation system, particularly for trucks, ships, and aviation, all of which are growing. So even if we have electrification of personal vehicles, we'll need biofuels for some of that. In the US, 10 years ago, we passed a set of renewable fuel mandates, and the prediction then was that by now we would have 5 billion gallons a year of cellulosic biofuels. This is what actually happened last year, and this little tiny blue line here is the actual cellulosic biofuels. That industry has been much slower to take off than was expected. It's getting there, but it's slow. Now, if we look at those cellulosic biofuels, it turns out that the growth has been rapid in the last 3 years, but it's been not liquid fuels, which are this small piece up here. That's been growing, but the bulk of it has been biogas that's being refined into renewable natural gas, so biomethane, and then used in transportation. And that growth has been phenomenally rapid. And this year and next year, we're going to see a lot more growth because there are many, many farms that are now putting in biogas digesters to take advantage of this opportunity. I'm also working with dairy farmers in Italy, where they have, in 5 years, 700 dairies have worked together to put up 400 digesters and are now displacing a gigawatt of electricity. So that's essentially the size of a large industrial coal-fired power plant. Not necessary because of farm recycling. We did that analysis for the United States, and interestingly, this is the total in terms of billions of cubic meters of biomethane that we could produce. The livestock piece is very important, but it's not the biggest part. The crop residues, the double crops, and our waste food and other landfill organic matter are all bigger than livestock. But what we believe is that the livestock systems can actually be the catalyst that can allow us to cost-effectively start to use all of these other biofuel, biomass alternatives. All right, I'm wrapping up. Just to very quickly point out, because in the United States, people care a lot about jobs. And there's been a lot of discussion about this transition from fossil energy to renewable energy potentially threatening jobs. And I just wanted to point out that when we do the calculations of how many jobs there are per energy unit, exajoules produced, that in fact, when we look at the conventional fossil energy options, they're typically between 10 and 26,000, but mostly 10 and 10,000 jobs per exajoule. This is where most of our electricity is right now. And the bioenergy options and the other renewables, especially wind and solar, have a tremendous number of jobs. This is Department of Energy data from the current US administration. And bioelectricity also has far more jobs than the alternatives. So this is a rural development alternative or opportunity as well as a renewable energy opportunity. So some of the advantages to biomethane I've already mentioned. It fits into our existing natural gas system. Half of the carbon is potentially available for carbon capture and sequestration or utilization. It burns clean at the point of use. The infrastructure's already been built by the fossil natural gas industry, so the biomethane, renewable natural gas industry can leverage all that infrastructure, and it can be quickly dispatched for electric demand, which actually makes it complementary to wind and solar. So we can use this dispatchable renewable energy from biogas to take care of our energy needs when the sun isn't shining at night or when the wind isn't blowing during the day. So it's potentially very complementary because it can be stored cheaply. Okay, so to sum up, in the United States, we are seeing rapid growth of wind, solar, and biomass. That is accelerating. There are many opportunities for agricultural development, and there are opportunities for more jobs in the energy sector than we have from our current technologies. And we have opportunities to do negative carbon energy in these systems and take advantage of photosynthesis to take CO2 out of the atmosphere. There are synergies that I didn't have time to talk with in depth, but we don't have to convert food cropland to make this work. We can take opportunities of niches in space and in time to make the system work well. Integrated systems that connect crops with livestock create tremendous opportunities for renewable energy. And in my view, sustainable energy supports sustainable agriculture. So we can get both of those goals achieved at once. I've got lots of collaborators. I'm not going to read their names, but this is work that's been done by many, many people, and we're working together to help to solve what I think is the greatest challenge of our time. Agriculture and forestry are a critical part of it, and I thank IPET for inviting me to share some of these ideas. Thank you.